In this lesson, we're looking at more inscribed angles, but specifically angles in inscribed quadrilaterals. So the Explorer activity that they have set up for us, they have this quadrilateral that's inscribed in a circle, and inscribed in a circle means that its four vertices are on the circle. And so the instructions were to measure the angles and find these sums. And so I've already done that. And I notice that's not an interesting number, that's not an interesting number. These are very interesting numbers. And so they want us to do it again, but have the center of the circle be outside of the quadrilateral. So that's what I did. And then I measured those angles. And once again, these are some very interesting numbers. Now I also have 180s here and here, but what we're looking for is what relationship existed here that also exists here. And so let's notice where those angles are. That's here, angles A and C, so opposite angles, and angles B and D, also opposite angles. Same thing's happening down here. Angles E and G are opposite angles of this quadrilateral, and so are F and H. So what conclusion can we make about the angles of a quadrilateral inscribed in a circle? Opposite angles of quadrilateral inscribed in a circle are supplementary. Based on our observations, does it matter if the center of the circle is inside or outside of the inscribed quadrilateral for the relationship between the angles to hold? No, it does not matter. It was shown to be true regardless of where the center is. So here it is as a theorem. If a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. So let's prove that. I'm given that I have a quadrilateral inscribed in the circle. I'm trying to prove that angles A and C are supplementary and B and D are supplementary. The union of BCD and DAB is the whole circle. Therefore, the measure of arc BCD plus DAB equals 360. Angle A is an inscribed angle, and its intercepted arc is arc DCB. Angle C is an inscribed angle, and its intercepted arc is arc DAB. By the inscribed angle theorem, angle A will be half of the measure of arc DCB, and angle C will be half of the measure of arc DAB. So the measure of angle A plus the measure of angle C equals 1/2 of the measure of DCB plus the measure, or 1/2, excuse me, the measure of DAB. And then in the next step, they say we're using the distributive property, and what we're actually doing is factoring the 1/2 out of these two expressions. So it's kind of like we're doing the opposite of the distributive property. And then back here, remember, we said that the measure of BCD plus DAB, which is the same as what we have here, is 360. So 1/2 of 360, which is 180. Therefore, angles A and C are supplementary by the definition of supplementary. And we could use a similar argument to show that angles B and D are supplementary. converse is also true, that if the opposite angles of a quadrilateral are supplementary, then that quadrilateral could be inscribed in a circle. So if we put those two statements together, we can get a biconditional statement. Now, a biconditional statement is an if and only if statement. So the beauty of a biconditional statement is that it goes both ways. What must be true about a parallelogram that is inscribed in a circle? Its opposite angles, both pairs, must be supplementary. So in number 4, I have a quadrilateral that's inscribed in a circle. I know angle P. Is it possible to find the measure of some or all of the other angles? Well, if it's PQRS, then I know angle P is opposite angle R. So the measure of angle R would equal 180 minus the measure of angle P. So I know that the measure of angle R would be 180 minus 57, or 123. As far as the other two angles, I can't find angles Q and S. There isn't enough information. Here, we're applying the inscribed quadrilateral theorem with some algebra. So I have this quadrilateral, and notice the first thing they want us to do is find the value of y. Well, I know that opposite angles of a quadrilateral inscribed in a circle have to be supplementary, so I notice that these opposite angles are given to me in terms of y. So I plug these two in here, I add them up and set it equal to 180, and solve for y. Then the instructions are to find the measure of each angle. Well, I've found the value of y, so I can just plug it in order to find angle P, angle R, and angle Q. I know that angles S and Q have to add up to 180, so 180 minus the measure of angle S is 63, and there's the 4 angles. Similar problem in part B. First, we're going to find the value of x by noticing that angle J and angle L have to equal 180 degrees. So 39 plus 7x plus 6x minus 15 has to equal 180. When I combine my like terms, I have 13x plus 24 equals 180. When I subtract the 24 from both sides, I have that 13x equals 156. And when I pull out my handy-dandy calculator and take 156 divided by 13, x is 12. So now we can find the measure of all of the angles that they gave me in terms of x. Angle J is going to be 39 plus 7 times 12, which is 123. Angle L is 6 times 12 minus 15, so 72 minus 15 is 57. Angle K is 20 times 12 divided by 3. So that's 80. I know that the measure of angle M plus the measure of angle K will equal 180 degrees because they are also opposite angles of the quadrilateral. Angle M plus 80, therefore, equals 180 degrees. So M is 100 degrees. In summary, angle J is 123, angle L is 57, angle K is 80, and angle M is 100. Similar problem in this your turn. I notice that the two opposite angles that I know in the diagram are U and W. So 37 plus 5Z plus 12Z minus 27 is going to equal 180. When I combine my like terms, I have 17Z plus 10 equals 180. 17Z will therefore equal 170 when I divide both sides by, when I subtract 10 from both sides. Z is 10 when I divide both sides by 17. So that means that the measure of the angle U is 12 times 10 minus 27. So 120 minus 27 is 93. The measure of angle W is 37 plus 5 times 10, so 87. Measure of angle T is 125 minus 10, so 115. And then the measure of angle V will be 180 minus the measure of angle T. So 180 minus 115 is 65. We've constructed an inscribed square before. Now we're using the properties of an inscribed quadrilateral to justify that construction. So remember how we did that. And I apologize that I do not have any functioning compasses left in my classroom. All of my good ones have managed to disappear over the course of the year. So remember that when you're doing this construction, you first use the compass to draw a circle. So again, I apologize that this is just a sketch, but you should be able to remember from module, I believe it was module 6, that we did this before. Okay, when you construct a circle using your compass, the point of your compass has already marked the center, which means you can draw a diameter, which is just a segment passing through the center, having endpoints on the circle. So here's A, B. When we construct the perpendicular bisector of segment AB, remember you're opening your compass up to a length a little bit longer than this. So maybe you would open your compass to this length and maybe do an arc like this. Same compass setting from B, and you'd have something that looked like this. And you'd connect the dots. And I apologize for how ugly this is, but oh look, they have a prettier version over here. So to show that ABCD is a square, we need to show that it has 4 congruent sides and 4 congruent angles. Because back in this construction, to finish the construction of the square, you would just connect these dots. So OA is congruent to OC, is congruent to OB, is congruent to OD, because they're all radii. I know that the measure of angle AOC is equal to COB is equal to angle BOD is equal to angle DOA, which is 90, because we constructed CD to be the perpendicular bisector of segment AB. And so these triangles are all congruent by side angle side. And therefore, all of these corresponding parts are congruent by CPCTC. So now we have to continue. We've shown that the quadrilateral has 4 congruent sides. Now we need to show that the quadrilateral has 4 congruent angles. If I use reasoning similar to what I did in the previous proof, I can show that triangle BOC is congruent to triangle COB. And you might be thinking to yourself, well, that's kind of silly, Mrs. Clouse, that's the same exact triangle. Of course it's congruent to itself. But notice the order. The order is very important. So if triangle BOC is congruent to triangle COB, then by transitive property, I can say that triangle AOC is congruent to triangle BOC. And that would mean that angle 1 is congruent to angle 4 by CPCTC. So then also by transitive property, if angle 1 is congruent to angle 4 here, and I already knew angle 1 was congruent to angle 3, that means angle 3 is congruent to angle 4. Notice that's these two angles of the triangle. I can use similar reasoning to eventually show that angle 1 and angle 2 are congruent, angle 5 and 6 are congruent, and 7 and 8 are congruent. We know that the sum of the angles in any triangle is going to be 180 degrees. So the measure of angle 1 plus the measure of angle 2 plus the measure of angle COA has to be 180. So that means, well, I already know angle AOC is 90. So angle 1 plus angle 2 plus 90 equals 180. That means angle 1 plus angle 2 is 90. And since those two angles are equal to each other, it can be concluded that angle 1 and angle 2 both measure 45 degrees. I can use a similar reasoning to show that the measure of all of these numbered angles, all of these, 1, 2, 3, 4, 5, 6, 7, 8, all of them measure 45 degrees. Therefore, the measure of each of the four angles of quadrilateral ABCD is the sum of the measures of two of the adjacent numbered angles, which is 90 degrees.